Hi, and welcome to our presentation. My name is Nick, and I work together with Alexander, Gabriel, and Pierre at Lab 1866, the internal innovation team at Mercedes-Benz. Today, we will discuss the development of fully autonomous vehicles, leveraging the technology of autonomous AI. During our presentation, we will introduce the context, explain the technical details, provide examples of relevant AI use cases, and give our final recommendations. We will explain our proposal throughout this presentation. We recommend Mercedes-Benz initiate rollout of large-scale pilot project consisting of a fleet of at minimum 300 vehicles. Mercedes should increase R&D investment to accelerate technological development of autonomous vehicles in anticipation of a drastic change in industry business models. Mary Barra, chairman and CEO of General Motors, stated her belief that the auto industry will change more in the next 5 to 10 years than it has in the last 50. New players are entering the market, the most famous examples being Uber, Tesla, Google, and Apple, all of whom have joined the race to achieve fully automated vehicles. Currently, there are no fully autonomous vehicles on the road. The number of partially autonomous vehicles on the road is very small at present, but is set to grow massively over the coming years. Research from the BCG Foundation shows that by 2035, 25% of new car sales worldwide will be automated vehicles. Furthermore, in absolute terms, the growth in sales of fully automated vehicles is set to increase significantly. As you can see in the second graph, by 2030, the vast majority of miles driven in the US will be by self-driving electric shared vehicles. This is not that surprising given the fact that the average vehicle is only used 4% of the time. Over the past few years, AI has exploded. The development of AI is linked to the development of machine learning and deep learning, which will be covered later on in the technical details part of the presentation. For the moment, we can define general AI as human intelligence exhibited by machines, machine learning as a method of learning and improving from experience, and deep learning as a subset of machine learning in AI that has networks which are capable of learning from data that is unstructured or unlabeled. When we speak of autonomous AI, we refer to artificial systems taking full control of decisions. Bill Gates said of automation that the first rule in any technology used in a business is that automation applied to an efficient operation will magnify that efficiency. The second rule is that automation applied to an inefficient operation will magnify that inefficiency. It is essential then that autonomous AI target identified pain points to solve an unsolved problem. Autonomous AI arrives when the cycle of decision-making is so fast that having a human in the loop is a liability.
Thank you, Nick. I will now provide an overview of the core technologies of autonomous vehicles and update you on the current state of our development at Lab 1886. We are focusing on three major fields: perception, behavior, and motion planning. To provide cars with a general sense of orientation and a template for the environment they are in, high-definition maps are used in combination with positioning systems such as GPS. However, the provided level of accuracy is not sufficient for autonomous driving. Therefore, multiple sensors around the vehicle are used to create a more detailed 3D model of the environment. These sensors include high-resolution cameras, radar, LiDAR, ultrasonic, and infrared sensors. The data from the sensors form the input for machine learning algorithms utilizing deep neural networks with unsupervised learning technologies to process and interpret the data. Multiple perception layers deliver a reliable object classification resulting in the identification of traffic signs, lane markings, and other actors. Fusing the interpreted sensory data with the mapping data achieves a more complete and reliable view of the environment. This forms the basis for autonomous driving technology. At Lab 1886, we have reached a high level of reliability in building an accurate view of the environment. Mastering decision-making and motion planning in complex environments, however, remains a challenge. I want to demonstrate this with an example. A self-driving car on an empty street is followed by another car. A child runs onto the street in front of the autonomous car. How does the car react? First, its sensors, cameras during the day, infrared at night, capture the image data. Machine learning algorithms, utilizing neural networks with multiple layers, process the image data. Through several layers, the algorithms are able to perceive colors, edges, shapes, and the contours of the unknown object. Putting this information together, the system determines that the object is a child. Additionally, the system calculates that the child will not move quick enough to avoid a collision at the current vehicle speed. The car needs to take action. It could brake immediately and with full force. However, the car behind it is very close and has a human driver. The driver will not be able to brake quick enough, crash into the car, and may suffer injuries. It is therefore necessary to predict the intentions, actions, and reactions of the other actors in the environment. The system needs to rapidly simulate multiple iterations of actor interactions and evaluate the probable consequences. Factoring in the time constraint, the system needs to take a decision about its next action. To do so, it must know the parameters that it should optimize for. This could be avoiding direct collisions with humans as first priority and avoiding car crashes as second priority. The system reaches a decision about its next action. Finally, it needs to execute the action. The system transmits a braking signal to the brakes that define all parameters such as force and length of braking. Here you see a framework that classifies autonomous vehicles based on the amount of driver intervention and attention required. It is a widely used industry standard. Currently, many of our models have reached level 2, partial automation. The most advanced cars are capable of level 3. This means the system is able to drive autonomously in specific use cases, such as highways with regular traffic flow. Whenever the system recognizes its performance limits, however, the driver needs to resume control. Our top-line Mercedes S-Type will be equipped with level 3 functionality at its launch in 2020. Level 4 automation requires the system to take all decisions in defined environments, such as one specific city. Within these environments, there is no need for a driver to resume control. Autonomous vehicles with level 5 capabilities do not need a driver, and consequently also no steering wheel. The system will be responsible for the whole journey in all environments.
Autonomous AI is already being deployed in businesses around the world, with companies looking to become industry leaders in the technology. Rio Tinto is one such company. It is an Australian mining firm which is focused on the extraction of minerals deep within the earth using various types of robot which incorporate AI. At the heart of their system is a state-of-the-art operations center which allows engineers to operate all mines, ports, and rail systems from a single location. There are specific aspects of Rio Tinto's mining process which are fully autonomous. Drill rigs are typically operated by human users who must be informed about the best places to dig, and all digging is done manually. However, Rio Tinto's drill rigs, which operate through autonomous AI, receive real-time data from AI instruments which aid decision-making intelligence. For example, the use of remote sensing data enables the machines to perform rock face identification and soil classification. Satellite imagery and drone-based monitoring helps the rigs to predict mineral prospectivity or locations of potential ores. Tracking systems allow the monitoring of ecological parameters, performing constant assessment of the impact of mining activities. Robotic devices take this information on board and perform their duties autonomously. Activities such as drilling, blasting, hauling, sampling, and rescuing are all done utilizing the AI instruments described, among many others. This creates an ecosystem of robots who improve through experience. This ability to assess impacts and potential in real time results in significant productivity gains. Amazon Prime Air is another case in which a company is making use of autonomous AI to enhance their business. Prime Air is a new project which Amazon plans to officially launch in the next few years, which involves the delivery of packages and parcels by drone. They have successfully trialed the service and competitors are already emerging in the nascent market. Amazon has stated their intent to control all drones from a central air traffic controller, similar to the operations center used by Rio Tinto. The process would involve a customer making an order from Amazon, which human laborers would then package as usual. This would be the extent of human interaction in the supply process, however. The drone would then pick up the package, make the delivery to the assigned location autonomously, and then return to the Amazon warehouse from which it originated. There are various dangers involved with autonomous drone flight. Amazon hopes to work with other drone manufacturers to establish a drone-only airspace, which would be too high to cause harm to those at ground level and too low to be in the way of aircraft. However, issues remain in takeoff, landing, and the risk of hitting birds and trees while in flight. To address the takeoff and landing related issues, the drones perform vertical maneuvers. Amazon hopes to enable its drones to warn people and pets to stay clear of areas where they would touch down to place packages. They also hope to implant facial recognition software to identify the recipient of the package accurately. To address mid-flight collisions with birds or trees, the drones have integrated cameras and sensors which allow them to dodge airborne instructions. This technology is labeled Sense and Avoid. Integrated GPS and sophisticated navigation tools will put drones back on track after unexpected avoidance maneuvers, such as large gusts of wind. Similar to the case of Rio Tinto, the service enhances the speed of delivery and the productivity gains on offer. They would also be able to function at all hours of the day. We propose the following areas of development for Mercedes-Benz. Firstly, you should look to enhance object detection through sensors to calculate distances and routes to their destinations, while being able to identify potential hazards. Algorithms predetermine actions, ensuring that a car drives into a tree rather than a person, or that a drone moves off route rather than hitting a bird mid-flight. Visual recognition, classification, and tagging allow robots to identify and group their environment. Rio Tinto's drill rigs use this to identify rock faces and soil, while predicting mineral proceptivity. Such technology could also be used in cars to ensure the person who has rented the car is the person in the driver's seat. Localization and mapping allows robots to follow a predetermined map and follow identified routes without veering off. Predictive maintenance allows machines to tell engineers when and how to update and repair parts. We identify 4 pain points addressed by automated vehicles. Firstly, they remove human fallibility by fully automating the entire ecosystem, where the priority of the algorithms is foremost to protect the passengers. Regarding efficiency, IoT sensors collect a vast amount of data, enabling the AI to produce the most energy-efficient ride from A to B. Additionally, the need for the human driver is removed, allowing passengers to maximize their time by completing other tasks instead of driving. Finally, through automation, the usage of cars can be redefined, performing deliveries and other tasks independent of whether people are inside. Mercedes will face challenges to pivoting toward automated vehicles. A successful implementation of AI in autonomous vehicles is contingent on the initial coexistence between autonomous vehicles and conventional vehicles. This may require key changes to road infrastructure. The pace of legal reform should increase to match the pace of technology. Laws must be created distinguishing the new liabilities of stakeholders, including the authors of the algorithms, manufacturers of the vehicle, and the passengers in the car. There must be a clear allocation of civil and criminal responsibility by law, where there is shared control between humans and computers. Autonomous AI represents a larger social transformation, where the machines become a new entity with rights and decision-making authority. This has serious ethical implications, as autonomous vehicles will need to perform life or death situations. Our final recommendations are as follows. Mercedes should roll out a large-scale pilot project with at minimum 300 vehicles to increase the amount of data collected. This data serves as an input for ML algorithms and trains deep neural networks to improve their decision making. It is crucial to understand that more data results in better decisions. They should also achieve partnerships with renowned academic institutions that are driving research in autonomous AI, for example, autonomous vehicle startup 5AI. Mercedes should cultivate relationships with suppliers of important technologies such as radar, LiDAR, IoT sensors, and hardware. NVIDIA, for example, has built up unique expertise in GPU-accelerated computing to accelerate deep learning applications. Finally, the company should seek cooperation and exchange of ideas with industry challenges such as Google's Waymo.